So, welcome to this second lecture of this course devoted to concentration of measure. So, during this second lecture, we shall study some basic inequalities. We shall prove some basic inequalities, which in some sense will be prototype of what we shall try to get in more general situations. So our nicer example, our simplest example of functions of independent variables is the case where this function is a sum of independent real valued variables. So the purpose of the game here is to study the behavior of the sums when you are recentering the sums. And so the purpose of the game is to build concentration inequalities of their centered sums around zero. So what we have in mind here is to use Chernov's inequality. And in order to be comfortable with the fact that Chernov's inequality is significant when the moment generating function exists in a non-trivial interval, so in order to be comfortable with that, we shall assume that the variables are very nice, typically bounded. So the case of sums is especially simple to deal with just because of the additive formula. We had already seen an additive formula for the variance, but we have the analog for the log of the moment generating function, which is also additive. And we have seen during the first lecture that Cramer's theorem ensures that at least in the large deviation regime, Chernov's inequality is optimal. So our efforts to build concentration inequalities will be to bound in a convenient way the moment generating function, and then simply apply Chernov's inequality to get tail bounds. The simplest approach amounts to try to bound the log of the moment generating function by the corresponding quantity for a centered Gaussian variable with some variance. So let us detail what we have in mind when talking about this kind of variables. So let's give a precise definition. A random variable which is centered at expectation will be said to be sub-Gaussian with variance factor V if for all lambda the log of the moment generating function of the variable is less than lambda square V over 2. And we shall denote by Sj of V the set of sub-Gaussian random variables with variance factor V. So the first comment is obvious. When you take when you take a normal variable, which is centered at expectation with variance equal to V, then of course, the random variable is sub-Gaussian with variance factor V, of course. The second comment is that since you have an asymptotic expansion of the log of the moment generating function when lambda goes to 0, it is equivalent to lambda squared the variance over 2. If it happens that the variable is sub-Gaussian with variance factor V, then you must have that the variance of Y is less than V. Of course, the variance does not need to be equal to V, it does not need to be close to V, but it has to be less than V. The third comment is that when you consider some independent variables that are all sub-Gaussian, then their sum is also sub-Gaussian with a variance factor, which is the sum of the variance factor. So it works exactly as the Gaussian property itself. And the fourth comment is that since we have already computed the function Legendre dual of the square function, we know that the dual of lambda square v over 2 is merely x squared over 2v. We may apply Chernov's inequality to a sub-Gaussian variable and get a tail inequality on the right side and also on the left side. So the left tail as well as the right tail is bounded by exponential minus x squared over 2v. That is what you can expect when you are looking at sub-Gaussian variables. You expect that their tails have also a sub-Gaussian shape. By the way, we could ask ourselves, well, why not taking as a definition the fact that the tails have this shape? It could be a reasonable definition of sub-Gaussianity. In fact, we have preferred to take as a definition the fact that we can bound the moment generating function by a Gaussian one. We have taken this definition because it is very convenient to see that with this definition, you have some kind of stability by convolution, exactly as in the the strictly Gaussian case. So this is the reason. By the way, there are several ways of defining sub-Gaussianity, and we shall see right now that there's different ways of defining sub-Gaussianity are in some sense all equivalent, at least if you are ready to lose some numerical constants in the definition of the variance factor, in some sense. So let's see that very precisely. So we have here a proposition. First, we have the thing that we have already seen, that is y belongs to the set of sub-Gaussian variables with variance factor v. You have the tail definition, which appears as a second statement. The third statement is a statement about moments, and the fourth statement is a statement about moment generating function, but not on the variable itself, but on its square. And you say that the moment generating function on the square is bounded by some constant, which I have decided to take as 2, but it could be 3. It would not change more the 6. Okay, so what we can see right now is that 1 implies 2, while 2 implies 3, with c, which is equal to 4 times v, and 3 will imply 1, with v equal to 4 times c. And finally, the fourth statement is equivalent to the third one by just taking convenient relationship between c and alpha. So in some sense, all these statements are equivalent, but you have to play with the relationships between these constants which appear, alpha, c, and v. But if you are ready to lose a factor 4, a factor 2, then all these statements are equivalent. So I think that it's good to see briefly how to prove that. So let's see that. So to see how 1 implies 2. 1 implies 2, this is simple. This is simply Chernov's inequality. This is what we have seen already. When you have a good control on the moment generating function, then it implies a good control on the tail. Okay, now let's see how the tail statement implies the moment statement. So here, this is about the tails, and here, this is about moments. So to do that, you can always assume that v is equal to 1, otherwise you change the variables, you take x equal to y over square root of v. You standardize the variable, okay? So if v is equal to 1, the computations will be easier. You just use Fubini to evaluate the moment of order 2k here. You evaluate it as 2k times the integral of the tail on the tail of the absolute value of the variable, because you have a square to handle here. And this is less than 4k times the integral of x to the power 2k minus 1 exponential minus x squared over 2 dx, just because of our 2 statements. And now you change the variable. You set x squared over 2 equal to t. And you discover that the expectation of y to the power 2k is less than 4k times the integral between 0 and infinity of 2t to the power k minus 1 exponential of minus t dt. And this is well known to be equal to some factorial. And this is equal at the end of the day to 2 to the power k plus 1 times k factorial. Okay, and this is this implies the statement number 3. So now to prove that 3 implies 1.
Excuse me?
The trick is to use symmetrization.
Monsieur, ça va remonter, s'il vous plaît?
Excuse me?
Can you re-explain the calculation? Because when you do the change of variable, I don't understand why it's k minus 1, because you say
you have when you change the variable, you have that x dx is equal to t. So you have a slight change in the powers because of that.
okay.
Okay?
Sorry.
It's just a change of variables. There is nothing very mysterious here. Okay? So now to see that 3 implies 1, there is a nice symmetrization trick to use here. And I give you the details because this is not the first time, this is the first time, but not the last time that we shall use the symmetrization trick. So what we are looking for here is simply a copy y prime of y, which is independent of y. And we consider the variable z, which is equal to y minus y prime. So this variable is symmetric around 0. And then you look at the moment generating function of the variable z. And we discover that in the symmetric case, this is very nice because you have just even moments which appear in the expansion. Lambda to the power 2k, expectation of z to the power 2k over 2k factorial. If you would have a look at the moment generating function of y itself, you have odd moments to consider, and these odd moments, you have nothing on it. So it's better to look at the symmetrized version because you have only even moments. And there's even moments, you have a good control on it, just because by convexity of the power function, you know that the expectation of z to the power 2k will be less than 2 to the power 2k minus 1. This comes from convexity. Times the expectation of y to the power 2k.
Monsieur,
Yes?
je ne peux pas comprendre pourquoi l'espérance de E puissance lambda z égale la somme. Pourquoi?
Qu'est-ce que tu ne comprends pas? Tu peux répéter?
Pourquoi l'espérance de E puissance lambda z égale la somme?
D'où ça vient? C'est le développement. So, what you do here is that you expand the exponential function, okay? And when you look at a symmetric variable, the expectation of z to the power, an odd power, is equal to 0.
Symétrique, c'est-à-dire E. Qu'est-ce que c'est symétrique?
La variable z est symétrique.
Pourquoi?
Parce qu'elle est la différence de deux variables qui sont indépendantes l'une de l'autre et qui ont la même loi.
Ok.
Donc, elle est symétrique autour de 0.
Oui.
C'est justement la raison précise pour laquelle on fait ce développement sur la version symétrisée de la variable et pas la variable elle-même. Ça va?
Ça va.
Okay, so I go on. We use convexity here just to bound the even moment of the variable z by 2 to the power 2k minus 1 times the expectation of y to the power 2k plus the expectation of y prime to the power 2k. But of course, these two quantities here are equal because you look at y prime, which is a copy of y. And so the expectation of z to the power 2k is less than 2 to the power 2k times the expectation of y to the power 2k. And we use the assumption
Monsieur, on utilise la convexité de quelle fonction pour obtenir cette inégalité?
On utilise le fait que quand tu regardes A plus B sur 2 à la puissance 2k, ceci est plus petit que A à la puissance 2k plus B à la puissance 2k sur 2. Et quand tu multiplies ça par 2 à la puissance 2k, tu obtiens la constante qui est ici, 2 puissance 2k moins 1. Ça va?
Ça va.
And so here we use the assumption to get that this is less than 2 to the power 2k c to the power k times k factorial. Okay. And now, when we go back to the expansion of the moment generating function, what we have obtained is that this is less than the sum between 0 and infinity of lambda to the power 2k over nothing times c to the power k, 2 to the power 2k, k factorial over 2k factorial. So we just have to check, this is easy, that k factorial over 2k factorial is less than 1 over 2 to the power k times k factorial. This is an exercise for you. And using this, we get that the exponential of lambda z is less than the sum of lambda to the power 2k times 2c to the power k over k factorial. And of course, you recognize the exponential of an exponential, which is merely the exponential of 2c lambda squared. And to finish the proof, we just have to notice that the moment generating function, excuse me, of z is nothing else than the product of the moment generating function of y at point lambda times the same but at point minus lambda. Since the variable y is centered at expectation,
Monsieur,
oui?
Je peux pas comprendre. To finish what? Cette inégalité, je peux pas comprendre.
Finish the proof.
Non, je peux pas comprendre. L'égalité en dessous.
Ah, l'égalité en dessous. Donc l'égalité en dessous, c'est simplement le fait que z is equal to y minus y prime. Remember that y prime is independent from y, and that the distribution of y prime is the same as the distribution of y. So this means that formally, the moment generating function of z is the product of the moment generating function of y.
Je comprends, c'est bon.
Okay?
Okay.
So, yes, what I was trying to say right now is that the expectation of y is equal to 0. So by Jensen's inequality, we know that the expectation of the exponential of lambda y is larger than 1. And of course, this is the same for minus lambda. So this means that when you have controlled this product, you have also controlled each factor of the product, just because of these inequalities here. And so the moment generating function of y is less than the moment generating function of z, and it is less than exponential of 2c lambda squared. And this means that y belongs to the set of variables which are sub-Gaussian with variance factor equal to 4 times c. And so this shows you that the statements 1, 2, and 3 are in some sense equivalent when you play with the various constants which appear in their statements. So now we have to relate the third and the fourth statement. So let us assume that for holes, so this means that for some alpha, the expectation of alpha y squared is less than 2. But of course, this implies that the sum starting from 1 of alpha to the power k expectation of y to the power 2k over k factorial is less than 2 minus 1, because I have not put the first term here. And this is equal to 1. And this means that, of course, we have a sum of non-negative terms here. So this means that each term is less than the total. This means that expectation of y to the power 2k is less than...
Monsieur, pourquoi vous avez écrit c'est égal à 1?
2 minus 1 equals 1. 2 moins 1 égale 1.
Pourquoi tu minus 1?
Pourquoi il y a un moins 1? C'est parce que ici, il n'y a pas le premier terme dans la somme. Le premier terme est égal à 1 dans le développement de l'exponentielle. J'ai fait exprès de le mettre dans le second terme, dans le second nombre, pardon. D'accord?
Oui.
So this implies that the exponential of y to the power 2k is less than k factorial times alpha to the power minus k. And so this shows that 3 holes with c equal to 1 over alpha. So now we have to prove the converse. If 3 holds, and this is very simple, you look at the exponential of the expectation of exponential of alpha y squared. You look at the expansion. Say that it is less than the sum of between 0 and infinity of alpha to the power k, c to the power k, times k factorial over k factorial. This cancels, of course. And if you choose alpha equal to 1 over 2c, you just see appearing the sum of 2 minus k between 0 and infinity. And of course, this is equal to 2. And you have finished the proof of the proposition. So the message here is quite simple. The message is that you have several equivalent ways of defining sub-Gaussianity in some sense. You can see sub-Gaussianity appearing on the moment generating function of the variable, on the tails, on the moments or on the moment generating function of the square of the variable. But anyway, there's different statements are all equivalent. So now let us see a non-trivial example of a sub-Gaussian variable. Of course, we have seen that the Gaussian variable is sub-Gaussian, but what's the point? It's interesting to see a non-trivial example. And the non-trivial example comes from Hövding's lemma. Hövding's lemma, which goes back to 1962, tells you that when you have a random variable y, which lays between a and b, which is bounded in some sense, and it is between a and b, then for all lambda, the log of the moment generating function of y, which has been recentered, is less than lambda squared times b minus a squared over 8. So in other words, the variable y minus its expectation is sub-Gaussian with a variance factor, which is exactly equal to b minus a squared over 4. So we do know, this was one of our comments before, that if the variable is sub-Gaussian, its variance has to be smaller than the variance factor. And so we know that the variance of y has to be smaller than b minus a squared over 4, at least if the result is true, at least if Hövding's lemma is true. And what is very surprising, and this is something that you shall derive again by using this beautiful idea that I like, that I love in some sense, is that you can use the change of probability to prove that the bound of the variance will be enough to prove the bound on the moment generating function. And it's just by magic, it's just because you change the probability, and the scheme of proof is as follows. You change you first prove, of course, the bound on the variance. Then you make the change of probability and you discover that under this new distribution, the variance is just the second derivative of the log of the moment generating function of the recentered variable. And then this means that the variance bound leads to a differential inequality. You integrate it and you get the result. This is the scheme of the proof. So let's see that in detail. So the proof of Hövding's lemma . So as I mentioned to you, we start with the variance bound. To make our life easier, we assume that the expectation of y is equal to 0. Otherwise, you change y into y minus its expectation. It does not change anything. And we consider step 1, that is, we want to prove the variance bound. So the variance bound seems something which is very simple to prove, but this is not quite the case. You have to be a little bit careful. If we go naively, if you are naive, we can just use the fact that y is between a and b and say, well, this implies, of course, that the absolute value of y is less than the maximum between the absolute values of a and b. And this in turn implies that the expectation of y squared is less than a squared sup b squared. And you use the fact that the variance is less than the expectation of y squared, which is less than a squared supremum with b squared. Pom, 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 pom. It does not work. So we are too sad. But in order to be happy again, it's important to realize what we have lost by using this bound on the expectation of y squared in order to bound the variance. What we lose when you do that is that the variance is not sensitive by a shift, is not sensitive to a shift, excuse me, of a constant on the variable y. That is, you can make exactly the same bound, but using y minus c instead of y. So why not doing that and trying to optimize on c? So let's try that. Let us introduce c to be chosen later. And use the fact that the variance of y is also less than the expectation of y minus c squared. And let's do exactly the same thing as before. That is, we say that y minus c lays between a minus c and b minus c. So we can say, just as before, that it is less than a minus c squared supremum with b minus c squared. Whoa, look at that. Here you can optimize this with respect to c. And if you try to optimize this with respect to c, this is very simple. The best that you can do is to take c in the middle between a and b. Okay, so you take c to be equal to a plus b over 2. And if you do that, then the variance would be less than b minus a squared over 4, and you are happy. Okay? So now let's turn to step 2, that is, we make the change of probability. So this is exactly the change of probability that we have already seen during the first lecture when we have proved Cramer's theorem. That is, we introduce p lambda, which is merely the exponential of lambda y divided by the moment generating function in order to make this a density times p. So this is the density with respect to the measure p. And we can compute, of course, the expectation of y under this new distribution. And this is merely the expectation of the variable y times the density and of course, this is also equal to the derivative of the log of the moment generating function of y. This is exactly what we have already used during the first lecture. And we go ahead. This time we consider the expectation of y squared, which is nothing else than the expectation of the variable y square times the density again. And you discover that this time the variance, which is nothing else than the expectation of y square minus the expectation of y square. There's two quantities we have computed them already, is equal to the second derivative of the variable y, of the log of the moment generating function of the variable y. So the variance bound that we have proved also holds, of course, under p lambda. The variable is still between a and b. It's not changing anything. And so you know that the variance under p lambda of y is less than b minus a squared over 4. And therefore, the second derivative of the variable, of the log of the moment generating function of the variable is less than b minus a squared over 4. You integrate this 2 times, and you get that psi is less than lambda square b minus a square over 8, because you have integrated 2 times. And when you integrate this, you use, of course, the initial conditions that psi y of 0 at 0 is equal to psi prime at 0 is equal to 0. This is, of course, always true, and this is true because the variable is centered at expectation. And this is the end of the proof of Hovding's inequality. So let's go on. Now, if you have independent variables which are bounded, then you can use Hovding's lemma to control the log of the moment generating function of each individual variable, and just use the additivity of the log of the moment generating function in order to get a result for the sum. And this result exactly says that the sum belongs to the class of sub-Gaussian variables with variance factor v, where the variance factor v is the sum of bi minus ai squared over 4. And so you get Hovding's inequality, which tells you that the tail this time is less than what you expect, that is the exponential of minus x squared over 2v, where v is the variance factor that we have made appear before. This is just because of our proposition. We already know that, which is a consequence of Chernow's inequality. And of course, the sum belongs to the class of sub-Gaussian variables. So this is Hovding's inequality. So what is nice with Hovding's inequality is that we have a control on the tail which is sub-Gaussian for all values of x. This is very nice. But of course, the price that we have to pay is that the variance factor can turn to be too large. It may happen that the variance factor is much larger than the variance of the sum itself. This is the price to pay. So let's see what it gives on the sum of Bernoulli variables, that is in the case of a multinomial distribution, a binomial distribution, excuse me. So in the case of the binomial, the sum has a variance which is exactly equal to np 1 minus p. And of course, we know that p times 1 minus p is less than 1/4. So this means that the variance factor which appears in Hovding's inequality is nothing else than the maximal variance when p varies between 0 and 1. So it is the worst case, but it's not surprising since we have a universal inequality. There is a price to pay. The price to pay is that it is not sensitive to the value of p. So it's optimal for p equal to 1/2, but it turns out that it can be very suboptimal when p is small when n goes to infinity. For instance, when p is equal to 1/n, you can lose a factor n in the variance factor, which is, of course, not very nice. Okay, so the message here is that, okay, Hovding's inequality is a very nice bound because it is a sub-Gaussian of the full range for all values of x, but the price to pay is that it may be suboptimal in terms of the variance factor. So this motivates the introduction of another inequality, which is Bennett's inequality, and which amounts to compare the log of the moment generating function with the same quantity for a Poisson variable, or more precisely, a recentered Poisson variable. So this is what you can try to do. So the idea is quite simple at the beginning. You just use the fact that the log of u is less than u minus 1 to bound the log of the moment generating function of the variable xi at lambda by the expectation of the exponential of lambda xi minus 1, just using this. And so this means that if you define the function phi to be equal to exponential of u minus 1, then this inequality here just means that you have a bound on the log of the moment generating function of the variable xi recentered here by the expectation of phi of lambda xi. And so this means that talking about the sum, the log of the moment generating function of the sum is less than the sum of the expectation of phi of lambda xi. And now we have to work in order to bound this quantity here. So note that this function phi, which is equal to exponential of u minus 1, is nothing else than the log of the moment generating function of a Poisson variable with parameter 1, which is recentered, minus its expectation. Okay? So this is the reason why we are on a good way, on a good path to get a sub-Poissonian bound. So now let's see how to prove this. let's see how to go from this to Bennett's inequality. Let's see what to do. So now we have to bound the expectation of phi of lambda xi. How to do that? Well, the trick is to use the fact that the function phi divided by x squared is non-decreasing. Of course, here you consider that the value at 0 at 0, you just take 1/2 in order to make this function continuous. So you have to check this. This is an exercise. Not that easy in some sense. So if you know that it is true, let's assume that it is true, then if you take a non-negative value of lambda, positive value of lambda, excuse me, and if you assume that xi is upper bounded by some constant b, then phi of lambda xi will be less than phi of lambda b times xi squared over b squared, just using the monotonicity of the function phi of x over x squared. And so this implies that the log of the moment generating function of the sum is less than the quantity that you have made appear, that is phi of lambda b over b squared, and times the sum of the expectation of xi squared. And so this time we have, when we take the dual, a lower bound instead of an upper bound, of course, and which is that this is greater than the sup of lambda x minus phi of lambda b over b times b squared times v, where v is the sum of the expectation of xi squared. And now if you set h to be 1 plus u log of 1 plus u minus u, h is the dual of phi. And you can compute everything with respect to h. The quantity which is up here, the sup of lambda x minus phi of lambda b over b squared times v is nothing else than v over b squared h of bx over v. So at the end of the day, what you get is that the dual of Sn is greater than v over b squared times h of bx over v. And this is what people call the Bennett inequality. Which is here. let's summarize, excuse me. Here, so Bennett's inequality, which tells you that the tail is bounded by a quantity which has a Poissonian flavor, because you see that this H function appear here. So you can ask yourself, did we get something which has the right flavor, that is, which is sub-Gaussian, at least in some range? The answer is yes, because you can easily prove that this H function is larger than U square over 2 times 1.
Monsieur, pouvez-vous montrer l'inégalité de Bennett encore une fois, merci. Je n'ai pas encore noté. Vous marchez trop vite.
Celle-ci?
Oui, je n'ai pas encore noté.
Alors, elle est dans les notes de cours, hein, ne vous inquiétez pas. Dans les notes de cours que je vous ai distribuées, elle figure en bonne place. OK?
OK.
So, it is easy to see that this H function is greater than this other function, which is easier to analyze and to interpret, because here, of course, you see that you have this alternative bound here, which is a consequence of Bennett's inequality, and that people ordinarily refer to as Bernstein's inequality. And here you really see that this inequality is sub-Gaussian in a range. That is, as soon as this term here is less than this one, then you have an inequality which has the flavor that you want, that is exponential minus x squared over 4v, let's say, not 2v, but 4v, if you stick in the range where bx over 3 is less than v. Okay? So this is an inequality which is sub-Gaussian in a range, exactly as we wanted to get. And the gain that we have with respect to Hoeffding is that this time we have the right variance factor. So this is what we have gained. So as a matter of fact, the last thing that I want to show you is that this inequality can be obtained under weaker conditions, just for free in some sense. So these weaker conditions are, instead of boundedness, we put control of on moments. So let us state Bernstein's inequality with these weaker assumptions. So here you have a control on the sum of the expectation of xi squared by v as before. And you have an extra control on the moment. Instead of boundedness, you ensure that the sum of the moment of the positive part of the variable to the power q, is less than something. And if it is true, then you have an upper bound which makes appear another function than h. It is called h1, and h1 has this shape here. But alternatively, if you make a change of variable in the inequality, you can write it like that. And this shape here is very convenient because you see exactly appear the same thing than before. That is, when this fact this term here is less than this one, you get exactly a sub-Gaussian inequality. So this is a very convenient way to write it. So let's see the proof of Bernstein's inequality. Let's see the proof. We restart from the same bound as before, that is the bound on the log of the moment generating function of the sun, which makes the phi function appear.
Excuse me, can you hear me?
Yes.
I'm not sure my micro works. Okay, I just wanted to ask, is the condition you showed above with the moments of the
Yes.
positive part of the random variable, is this the same as the sub-exponential condition, which is classical for Bernstein's inequality?
It's weaker. It's slightly weaker.
Okay, so the
I will show you that afterwards, okay?
Okay, thanks.
Let's go on with the proof, and afterwards I will show you that it is slightly weaker. Yes, this makes the function phi appear, and we use again the fact that the function phi has this monotonicity, but in a different way. We use it in order to say that phi of u is less than u squared over 2 for all values of x which are non-positive. Yes, that's it. And so this means that phi of u is less than u squared over 2 plus the sum for k greater than 3 of lambda to the power k over k factorial, I'm expanding the exponential here, times the positive part of u to the power k. And this is true for all u. For positive values of u, you have the full expansion, and when u is negative, you just have this first term. So you just have to integrate this expansion to get a bound on the log of the moment generating function of the sun, which is merely lambda squared over 2 times the sum of the exponential of xi squared, which comes from the first term of the expansion. And then you have the other terms of higher order, which make the moments appear the moments of the positive parts of the variables. Okay? And now we use our moment assumption. And you see that psi Sn of lambda is less than lambda squared v over 2 times 1 plus the sum k larger than 3 then of lambda to the power k minus 2 times c to the power k minus 2. And this here is exactly equal to lambda square V over 2, 1 minus C times lambda, at least, of course, if this makes sense, that is, if lambda is less than 1 over C. And now to conclude, it remains to optimize with respect to lambda in the interval 0, 1 over C, lambda x minus lambda square V over 2, 1 minus C lambda. And it is easy to see that it is equal to V over C square, H1 over Cx over V. And this is exactly the result that we have stated before. That is, we have proved Bernstein's inequality. So let's see that the conditions that we have here, the moment conditions, are indeed weaker than boundedness. If the variables happen to be bounded by some quantity V, as in the statement of Bennett's inequality, then of course you can readily see that the moment of the positive part of the variable are less than V times B to the power Q minus 2. And this is in turn less than this quantity here, just because the power 3 to the power, the quantity 3 to the power Q minus 2 is less than Q factorial over 2. When you look at this, the worst case is Q small, that is Q equal to 3, and for Q equal to 3, this is an equality. And after that, it's easier to fulfill the inequality. So the moment condition holds with C equal to B over 3, so you can exactly recover the statement of Bernstein's inequality that we had before, because its H1 function is also greater than U squared over 2 times 1 plus U, exactly as the H function. So here the lesson is everything is exactly the same as in Bennett's inequality, but you have this H1 function which appears instead of the H function. And this H1 function locally has approximately the same behavior, but when U becomes large, it is linear with respect to U instead of being U times log as in Bennett's inequality. This is the difference between the two. But otherwise, both inequalities lead to sub-Gaussian inequalities in a range. Let's see why. It's very simple. H as well as H1 have the property that they are, when you divide by U squared, they are non-increasing. So this means that when you look in a range here, when U is less than U0, then G of U is greater than the square times the value of the function at U0. And so when you look at Bennett's inequality, for instance, this means that when X is less than V over B, then the tail is smaller than sub-Gaussian 1 with a variance factor which appears, which depends on V, of course, but also on the value of H at point 1, but which is a constant, it's a number. But you have it in this range here. And for the Bernstein case, it's exactly the same, but this time, this is the H1 function which appears, and its value at 1 appears as well as before the value of the h function was appearing. But it's exactly the same, and the range is this time x less than v over c. So let us finally see what it means when we normalize as in the central limit theorem. If you normalize as in the central limit theorem, if you are in the conditions of the central limit theorem, that is, you have variables which are ID, then and centered, then the V here is equal to n times the expectation of x1 squared, so n times the variance, the common variance of the variables. And so if you take x to be equal to theta times root n, as you have to do that when you look at the central limit theorem normalization, then you discover that the range on which the inequality holds true is theta less than root n times exponential of x1 squared over b. So as CB as a 1, 2, something like that. This means that the range is very large. This means that theta has to be less than square root of n in order to get a sub-Gaussian bound. So this means that you have much room for this sub-Gaussian inequality to hold. The central limit theorem regime is theta tends to infinity. Theta is fixed, excuse me, and n goes to infinity. Here, you have the possibility of taking a very large value of theta as compared to n, and you still have a sub-Gaussian inequality on the tail. Okay, so you see the gain that we have obtained with respect to asymptotic the asymptotic central limit regime. Okay, so that's all for the moment. I propose to take a coffee break during, let's say, 5 or 10 minutes. And after that, we shall pass to the second part of today's lecture, which will be devoted to the control of the variance of a function of independent variables. So coffee break. So let's turn to the second half of this today's lecture. And let us begin with the issue of bounding the variance of a function of independent variables. So the inequality that we shall see today is Efronstein inequality, and I would like to explain to you how to prove this very beautiful inequality. So let's take a function of independent variables. Why are we interested in bounding the variance? Well, there are two reasons. The first one is that it's an interesting issue by itself, since by Chebyshev inequality, it gives you a first concentration result, which is not as sharp as an exponential one, of course, but anyway, it's an interesting result by itself. That's one point. The second point is that it paves the way to prove more complicated inequality, more sophisticated inequalities that we shall prove afterwards. So in some sense, it's interesting by itself, but it's also a way of discovering what are the right paths to follow in order to prove concentration inequalities. This is the first issue in some sense. So as we have seen, the way we have studied the sums of independent variables was to use in a heavy way additivity This is true for the variance and for the log of the moment generating function as well. Okay, so really for this case of sum, there is something very specific which happens. So the first thing that we could try to do in order to deal with much more general objects, that is functions of independent variables, the first attempt, I would say, would be to try to keep this additivity. So how can we do that? When you look at what it gives, how do you prove, excuse me, additivity for the variance, you really see that independence itself does not play a role. What is playing a role is the fact that you have orthogonality between the variables, okay? So you can try to keep this orthogonality just by using a trick, which is that a function of independent variables, you can expand it as an orthogonal sum just by using Martingale decomposition with respect to Dup's filtration. So that's what we are doing right now. We are doing a Martingale decomposition. So how does it work? You simply consider the sigma fields generated by the first variable, and you take the expectation conditionally to their sigma fields. So concretely, this means that given y between 1 and n, you take expectation sub y to be defined as the expectation conditionally to the sigma field generated by the first variables up to index y. You take the convention that A null is just the expectation itself. In some sense, it is the expectation conditionally to the trivial sigma field. And then you look at the increments, which are simply the difference between AI z and AI minus 1 z. And you look at the expansion, z minus its expectation equal to the sum of these increments. So this is very simple, nothing to say. For the moment, I have just used simple algebra. So now at this stage, I will use the Martingale argument. I shall use the fact that the variable delta I have, of course, some structure with respect to this conditional expectation. And what I want to use as an argument is that the products delta I, delta j will be centered, and more precisely, they will be centered conditionally, and then afterwards, of course, if they are centered conditionally, they are centered at expectation. So how does it work? I take some index j, which is larger than the index I, and I just compute the expectation conditionally to the variable up to variable I of the product delta I, delta j. So at first glance, it is easy to see that I can put delta I in front of this expectation just because delta I is measurable with respect to the sigma field I am conditioning by here. And after that, I simply use the fact that the sigma fields are included one in each other to notice that when I compute the expectation conditionally to x1, xi of z, zj here, then it is equal to the expectation of conditioning to x1, xi of zj minus 1 also. And these two quantities are all equal to the expectation conditionally to x1, xi. Just because the sigma field generated by x1, xi is included in the sigma field generated by the variables x1 up to xj minus 1. Okay, so this means that when I compute now the expectation of delta j conditionally to x1, xi, it is of course the difference between these two expectations. There's two conditional expectations, but these two conditional expectations are both equal to the same guy, which is this guy. And so this is equal to 0. So the products delta I, delta j are centered conditionally to the sigma field generated by x1 up to xi. And so they are centered. So these increments are orthogonal in L2. And so this is enough now to imply that the variance is merely the sum of the expectation of delta I squared. Notice here that independence does not appear at any stage. I have just used the fact that the sigma fields are included one in each other. Okay? This is a pure Martingale argument. No independence at this stage. But of course, this is not quite the end of the story, because now the issue is how can we deal with these guys here, this expectation of delta I squared. And it's a fact that these guys are not that easy to compute because they depend on calculation with respect to many variables at the same time. And so the gain that we have with respect to the initial problem is not that clear. We would prefer to get some bound which makes some variable per variable computation appear. That is, we fix all the variables but one. So this is exactly what we shall do right now. We shall make appear another type of sigma field, another type of conditioning, and we introduce the random vector, which is composed by all the variables except variable xi. So I take the vector x1, xn, and I remove the variable xi. And I'm looking right now to the expectation conditionally to this vector x bracket I here. And making the calculation of this expectation amounts to fix all the variables but xi and to compute an expectation in this very coordinate number I. Okay? And now, turning to the sigma fields, we shall really use independence and we shall pass from the additivity idea to the subadditivity idea. And this subadditivity idea will be very, very, very important for what follows, not only for today. So let's see what is the relationship between this conditioning and the initial one, that is the conditioning with respect to the first variables. So this is very easy to compute because we are in the case where the variables now are independent. We use really independence. And you see that computing a conditional expectation when you have independence, this is very easy. This is just integrating with respect to the variables you have not conditioned by.
Très bien. J'ai trouvé ceci sur le web. This is just integrating.
Okay? So this means that when you compute the expectation conditionally to the first variable, you just have this integration here with respect to the variables which are active in the integration, that is the variable number I plus 1 up to n. So we integrate with respect to these variables. and the others, of course, are fixed. Now, talking about the other conditional expectation, when you condition by all the variables but variable number y, then it is very simple. You just integrate the function j here with respect to this single variable. So you have a one-dimensional computation to do. Okay? And now when you combine both, it gives you the fact that if you first make this computation and afterwards this one, this amounts to compute the conditional expectation with respect to the first variables up to I minus 1. Because you see here that first you integrate with respect to this variable, and then you integrate with respect to the others. So you have integrated with respect to all the variables, but the first one. Okay, so this means that you have a way of computing the expectation conditionally to x1 up to xi minus 1. And so now this means that using this calculation here, you may interpret the increment delta I as a conditional expectation of the variable z recentered conditionally to x bracket I. And this is very important because as soon as you have done that, you can use Jensen's inequality, conditionally, of course. If you use Jensen's inequality conditionally to x1, xi, then this means that delta I square will be less than the expectation conditionally to x1, xi of the initial variable square. And so this means that when you take the expectation, of course, the expectation of the conditional expectation just gives expectation of the quantity which appears here and which is z minus expectation conditionally to x bracket z of z. But of course, this is also equal to the expectation of the conditional variance, okay? Because here you can always, for free, introduce the expectation bracket I here. This is for free. And so this makes appear the conditional variance. And at the end of the day, you have bounded your variance by the sum of the expectation of the delta I square, and they are themselves bounded by this expectation of the conditional variance, and you get Efronstein's inequality, which tells you that the variance is always less than the sum of the expectation of the conditional variance. And now you are happy with that because the quantity here that appears, this quantity is just a computation in one variable, okay? You freeze all the variable but variable xi, and you integrate with respect to this variable xi. So you have a one-dimensional computation to do. And this makes you happy. So to use this Efronstein inequality that you can use in many, many examples, it's good to rephrase or rewrite the variance that appears in the right-hand side of Efronstein's inequality. So the right-hand side of Efronstein's inequality has this shape here. And you can rewrite it in different forms just by using that the variance can be expressed in very different ways. You can use the interpretation of the variance as a distance between the variable and the space of constants in L2. So this is here, this interpretation. Or you can use also the symmetrization trick, which amounts to interpret the variance as 1/2 of the L2 square distance between y and an independent copy of y that I denote by y prime. And of course, by symmetry, it's also equal to the expectation of the positive part of y minus y prime square. So if you do the same computations, but this time conditionally to x bracket I, this gives you two different ways of expressing the variance. On the one hand, you can say that the variance appearing, the right-hand side which appears in the variance bound in the Differential inequality, this right-hand side can be expressed as the infimum over the variable zi here, which are x bracket I measurable, because the x bracket I measurable random variables play the role of constant, okay, when you condition by xi. And this is this is equal to the infimum of the sum of the expectation of z minus zi squared. So this is the first interpretation. The second interpretation comes from the symmetrization trick. Yes? A question? No question. Okay, so if you use the symmetrization trick, you introduce a copy of all the variables. So you denote it by x prime 1, x prime 2, x prime n. This is a copy which is independent of the variables, the initial variables, x1, xn. And you introduce z prime I, which is simply the function of all the variables as before, but you have substituted x prime I at the very place where before you had xi, okay? And then the right-hand side of differential inequality can be interpreted as 1/2 of the sum of the expectation of z minus z prime I squared, or alternatively, also by symmetry conditionally to xi, alternatively, it can be expressed as the expectation of z minus z prime I positive part squared. So now let's see some applications of Reifenstein's inequality. As I mentioned before, there are two ways or different angles to see differential inequality. First, you can see it as a prologue of a more general machinery that we shall develop afterwards. But it's also interesting by itself. It is another angle of view. It is a versatile and powerful tool for dealing with many applications. So we first see what are the kind of applications that we can deal with differential inequality. So the easiest one is to produce a variance bound for functions which have the following structure. They fulfill the bounded differences condition. So what does bounded differences condition mean? It means that when you move in one variable, in the xi coordinate, for instance, you cannot move from more than a quantity which is ci, okay? So in some sense, you are exactly in the situation as in Hölderlin's lemma, okay? But when you move in one variable. Equivalently, you can see this condition as some kind of a Lipschitz condition. If the Ci were all equal to some quantity C, this would say that the function f is C Lipschitz with respect to Hamming distance. Hamming distance is just the quantity which appears if I remove the Ci here. This is Hamming distance. Okay, so this is some kind of convexified, weighted Hamming distance, I would say, and you are one Lipschitz with respect to this weighted Hamming distance. So this is some kind of Lipschitz condition. Okay. Now, as I mentioned already, this means that if you change the coordinate number I, keeping all the others fixed, the value cannot change by more than Ci. Yes?
Pourquoi vous enlevez CI? CI. Pourquoi vous enlevez CI?
Alors, j'enlève C, je ne l'enlève pas. Je dis que si je l'enlève, ce que j'obtiens, c'est une quantité qui est connue pour s'appeler la distance de Hamming. OK? J'enlève CI, ça c'est la distance de Hamming, Hamming distance. Donc, ce qui apparaît ici, c'est une distance qui ressemble à la distance de Hamming. C'est une version pondérée de la distance de Hamming. C'est ça que je dis. OK? So now, this is the very situation where you can apply Hoeffding's lemma conditionally to X bracket I, because you are exactly in the framework of Hoeffding's lemma, conditionally to X bracket I. When you freeze all the variables but variable number I, then you see that this variable, which is active with only one coordinate here, lies in some interval with Ci. So the length of the interval is Ci, and so using just Hoeffding's lemma in its weak conclusion, just on the variance, we do not use for the moment the full conclusion on the moment generating function, just use the variance inequality, then you get that the variance conditionally to X bracket I is less than Ci over 4. And if you combine this with Efronstein's inequality, then you get a bound on the variance as soon as this bounded differences condition hold. So let's see some example where you can easily use this framework. Let's come back to the example of bin packing. If you look at the example of bin packing, then you see that if you change one variable, then it will change the size of the minimal length of admissible covering just by 1. If you change one variable, the number of bins that you need will just change by 1 and no more than 1. So this provides you for free a bound on the variance. The variance is less than n over 4. And generally speaking, if you do not say more on the distribution of the variables than they are IID, you cannot improve on that, because when you look at the situation where the variables are Bernoulli, they are equal to 0 or 1 with probability 1/2, then the variable z corresponds to the sum of the xi variables, except on a very special situation where the variables are all equal to 0. But apart from this very special situation, if you think to the optimal covering in this case, it's very easy to describe. You need exactly one bin each time you have a variable which is equal to 1. So this means that the optimal covering has a number of bins which is equal to the number of variables which are equal to 1. The only special case is the case where all the variables are equal to 0 and where you need one bin to put them all. Okay, so this means that Z is almost a binomial variable, okay, except on a very special event, which has a very small probability. And by the way, this means that the variance in this case is equivalent to n/4. So you cannot expect to improve on the variance bound that you have got in this case, at least if you do not say more about the distribution of the xi. If you consider the longest increasing subsequence, the story is about the same. That is, if you change one variable, then you just change by the number, the optimal number of an increasing subsequence, the maximal length. You will change it by no more than 1. Okay, so exactly as before, you get a variance bound on Z, which is the variance of Z less than n/4. This is the same conclusion. So here, this variance bound is known to be suboptimal. The right order for the variance is n to the power 2/3, but it is a very difficult result to obtain. But nevertheless, even if the variance bound here is suboptimal, it is enough to prove that the variable concentrates around its expectation because the expectation is of order n. So this means that the order of the expectation is n, while the order of the standard deviation is root n. So n versus root n, okay, this means that the expectation is much larger than the standard deviation. So this says by Chebyshev that the variable concentrates around 0 when you subtract the expectation. Okay. Now, if we go to empirical processes that you can write this way, you have, in some sense, an array of variables. Okay, so you have random vectors which are independent, the xit, and you look at the soup of the sum of the xit. And if you assume the xit to be between ai and bi, you can exactly use the fact that the bounded differences condition will hold with ci to be equal to, excuse me, there is a mistake here. This is, the square is not there, or it is there. This is ci square equal to bi minus ai square. And so the variance will be less than the sum of the bi minus ai square over 4. So this is a very easy bound to obtain, which is of course not improvable if in the situation where the variable are Bernoulli with parameter 1/2, as we have already seen, but which can be improved in other situations, of course. But in some situations, it cannot be improved. It is interesting to see what it gives in the special case where the xit are equal to numbers, alpha it, constants, times random signs. Random signs which are independent and which are equal to +1 with probability 1/2, -1 with probability 1/2. So in this case, we get what people call Radmacher processes. And for Radmacher processes, we get as a bound here the variance is less than the sum of the sup of the alpha I t square, just because remember that the difference between +1 and -1 is equal to 2. So to the square, it gives you 4. And so you have the 1/4 which cancelled with this 4. So in this case, you get this bound. And you could wonder whether you could improve on this bound by commuting the sup and the sum. In some sense, it would be much more natural, because when you look at the situation where you have just a single t, the variance is equal to the sum of the alpha I t square. So you would expect that when you look at the variance of the sup, it would be of the order of the sup of the variance. It would be nicer. So it can be done at the price of losing a factor 2. And it can be done by using Efronstein in a better way than we did just by using the bounded differences condition. So now what we are trying to do is to go beyond the bounded differences condition and see that Efronstein's inequality can be used in a more clever way in some sense. So talking about Rademacher processes right now, what we can do is as follows. I'll try to explain you this and take time to explain you, because this kind of proof, we shall do it again and again in the future. So look at the argument that we shall use. So let's take Efronstein's inequality in the version when you look independent copy of the initial variable. So we take epsilon1 prime, epsilon prime n, independent from epsilon1, epsilon n, and epsilon prime is a copy of epsilon. So let's take the quantity of interest, which is the sup over t of the sum of alpha I t epsilon I. This is in quantity of interest. We are dealing with a finite set capital T, so there is no problem. This is equal to the sum of alpha I t star epsilon I for some t star. Which of course depends on epsilon 1, epsilon n. And now we introduce the variables z prime I, which are simply defined as I take this function here, but I change epsilon I into epsilon prime I. So this is the sup of the sum with j different from I of the same quantity as before, that is alpha j t epsilon j, but at the place number I remove epsilon I and I replace it by epsilon prime I. So this gives us alpha I t epsilon I prime. Okay, here let's make the change. And of course, the trick now is to say that it is always greater than the value of this quantity at any t. But those t include t star. So this means that it is always greater than the quantity which is there for t equal t star. T star epsilon prime I. But now, if you subtract z prime I to z, since z prime I is greater than this quantity, the difference between the two will be less than the difference between z and those guys. But who is z? Z is the same sum as here, but for all j. So this means that the difference between the two will make this term cancel. And so you will end up with alpha I t star times alpha epsilon I minus epsilon prime I. Okay, but now you see the power of the symmetrization trick, because I do not have to control z minus z prime I, but I have to control z minus z prime I positive part. So it is enough to have controlled it from above. So now, when I look at the difference between z minus z prime I positive part square, I can say that it is less than alpha I t star square times epsilon I minus epsilon prime I square. And now it remains to evaluate the expectation of that. But to do that, I first do it conditionally to epsilon 1, epsilon n. And if I do that conditionally to epsilon 1, epsilon n, z minus z prime I positive part square, conditionally to epsilon 1, epsilon n. This means that I have to compute the expectation of this guy conditionally to epsilon 1, epsilon n, but conditionally to epsilon 1, epsilon n, the expectation of the cross products is equal to 0 because the epsilon prime I are centered and independent from epsilon I. So this makes just some factor 2 appear times alpha I t star square. And now it remains to upper bound this by the sup of the alpha I t square. Okay, so this means that the variance of z is less than 2 times the sup of the alpha I t square. This is what we have obtained. Okay, so let's come back to the slide. So we have proved this. And to see that we have gained something with respect to the preceding inequality, let's look at the situation where the alpha I t are equal to 1 if and only if I is equal to t, otherwise they are equal to 0. This is a case where t itself is the set 1, 2, etc. Until n. So in this case, you really see that the sup of the sum of the square is equal to 1, while the sum of the sup is equal to n. So you have gained a factor n on this bound with respect to the previous one. So you see that this more clever way of using F1T's inequality provides us potentially a huge gain. The sup of the sum can be much smaller than the sum of the sup. This is the message here. For non-negative empirical processes, we can also use a trick, another trick, in order to get a better bound than just using the bounded differences condition. If you use the bounded differences condition in the situation where the xit are non-negative and less than 1, then you get the crude bound coming from the bounded differences inequality, in which is variance of z less than n/4. But if we use Efronstein's in a more clever way, what we can prove, in fact, is that the variance is less than the expectation, just as for a Poisson variable. Okay? Let's see why it is so. Let's see how to prove that. So again, let's take Z to be the soup of the sum of xit. And let us write it as the sum of xit star. Okay? And now let's take the other interpretation of Efronstein's inequality, and let us introduce x bracket I measurable variables. Namely, let us introduce zi, which is simply this quantity, but where I will put the xit variables equal to 0. So this means that I look here to the soup over T of the sum of j different from I of xjt. And I have replaced the xit variables by 0. Okay? So I do exactly the same thing that I have done before. That is, I say that zi is for sure larger than the sum for j different from I of xjt star. So this means, of course, that z minus zi is non-negative for sure, but it is less than xit star. And so, which is less than 1, by the way. So when you look at the sum of z minus z prime I squared, the very nice trick is that it is less than the sum of z minus zi just because the quantity here are between 0 and 1. But since I know something which is sharper than that, that is, I know that the difference between z and zi is less than xit star, this is less than the sum of xit star, which turns out to be equal to z. And therefore, you have proved that the expectation of the sum of z minus zi squared is less than the expectation of z. And Efronstein allows you to conclude that the variance is less than the expectation. So this means that this variable behaves like a Poisson variable in some sense. The variance is less than the expectation. So as we shall see later on, this example is a special example of what we shall call self-bounding functions, and for which the variance bound that we have obtained here will hold. Okay. So the case of random matrices, you can look at it also, though I remind you that in this case, you look at some triangle array of IID variables, and you consider the symmetric random matrix, which entries correspond to this array under the diagonal. And then you consider the largest eigenvalue of this random matrix, and you can interpret it as the sup of U transpose AU over the unit sphere of Rn. And now, if you assume that the variables xij are all less than 1, using the same kind of argument as before, when we have controlled the Ramacher processes, you can prove by using Efronstein's inequality that the variance is less than some numerical constant, something like 16 or something like that. Okay, this is done in the notes, and I leave you this as an exercise. It's a good exercise for you. And that's over for today. That's enough. Now I say hello to you and see you next week.